Today, we're going to peel back the cover on our everyday gadgets to see how they actually spring to life. We're talking about the very first instructions a simple electronic chip ever gets. So let's dive right in.
I mean, really think about it. Or how your TV remote knows exactly which button you just mashed. It feels like magic, right? But the reality is actually way more interesting.
You see, at the heart of almost every one of these devices is a microcontroller. It's basically a tiny, dedicated computer brain. But a brain is pretty useless without thoughts. And for a chip, those thoughts are a set of instructions we call firmware.
And that's what we're going to do today. We're going to follow that entire journey, step by step, to see how a human idea gets translated into the language of silicon.
Okay, so imagine you have a brand new piece of hardware, a fresh chip right off the line. It's a blank slate. It can't do a thing. The very first job is to give it instructions, to provide the firmware that will become its permanent set of rules for life.
Now, the key word here is permanent. Unlike the apps on your phone that you can install and delete whenever you want, firmware is burned directly into the chip's memory. It's the rock-solid, fundamental set of instructions that doesn't just disappear when you turn the power off.
So, to write this all-important firmware, a programmer needs a specialized workspace. You can't just type this stuff into a Word document. You need a digital workbench where the code is written, tested, and prepped for its big journey to the chip.
And this is what that command center looks like. This is MPLAB, a pretty common integrated development environment, or IDE. Now, I know it looks a bit intimidating. You got windows everywhere, tons of text, but trust me, each little part has a very specific and very crucial job.
Let's break this beast down, shall we? The main area, that's the editor window. That's where the programmer is actually typing out the commands. Then you have the special function registers window. Think of that as a dashboard for the chip's brain, showing the real-time status of everything inside. The simulator and stopwatch let you test drive the code virtually to squash bugs early, and that message window at the bottom, it's your report card. It tells you if your code translated successfully or, if you made a typo. Okay, here's the really crucial part. A microcontroller doesn't understand any of that text a programmer writes, not a single word. The only language that chip speaks is the binary language of ones and zeros. That's it. So, to make this translation easier, programmers use something called mnemonics. Just think of them as nicknames or shorthand. Instead of having to remember a crazy binary sequence like 000111 and what it does, you can just write a short command like BTFSS. It's so much easier for a human brain to work with. And the special tool that does this translation is called an assembler. It's a program that takes the programmer's file, which is full of all these mnemonics, and it just methodically goes through, line by line, and converts each one into its machine code equivalent. It creates the final file that the chip can actually run. And this table right here illustrates that translation perfectly. That one human command, BTFSS port D 0, gets broken down by the assembler into these distinct binary parts. You got the opcode, which is like the verb. It's the action. The file register is a noun, the place you're performing the action, and the bit is the tiny little detail. Together, they form one complete, perfect instruction for the chip. Okay, so the code is written, it's been assembled into machine language. Now for the physical part. How do we get that code from the computer onto the actual silicon chip? Well, for a long time, the process was, honestly, a bit clunky. It involved physically taking the chip out of its circuit board, sticking it into a special programming unit to get the code, and then putting it back. As you can imagine, that was slow, and you always risked bending one of those tiny little pins. The modern way, though, is so much more elegant. It's called in-circuit debugging, or ICD, and it's a total game changer. It lets a programmer connect their computer directly to the chip while it's still sitting right there in the final product, like inside the coffee maker prototype. You can upload new code, run it, stop it, check things in a real-world environment. It is a massive leap forward for development speed. Writing code that just works is one thing, but writing code that's clean, understandable, and easy to fix later on, that's a whole other level of skill. Just like building a house, you absolutely need a good blueprint. A really well-structured program is always organized into these logical blocks. You start with a header comment that says who wrote it and what it's for. Then you configure the chip's basic settings, define your shortcuts, and get all the hardware ready to go. Only then do you dive into the main program loop and all its little helper routines. This organization makes it possible for someone else, or even you 6 months from now, to actually understand what's going on. And before they even write a single line of code, programmers will often map out the entire program's logic using a flowchart, just like this one. It's a graphical blueprint. Diamonds are for decisions, rectangles are for processes. It helps you visualize the entire sequence and catch any weird logical errors before they ever become code.
Now, everything we've talked about so far has been assembly language. It's very direct, very low level, but it's also incredibly detailed and really specific to each family of chips. So you might be asking yourself, surely there's got to be an easier way, right? And the answer is a big yes. Meet the C programming language. It's what we call a higher level language because it hides a lot of that nitty-gritty detail. A single line of C code can do the work of many lines of assembly, which makes it feel a lot more like you're writing a logical set of instructions in English. So let's put them head to head. Assembly gives you the ultimate, down-to-the-metal control. You can create incredibly small, super efficient code. But it's tough to learn, and it's tied to one specific processor. C, on the other hand, is just easier to read and write, which means you can develop things way faster. And the real kicker? The same C code can often be reused on totally different chips. It's way more portable. But there's no free lunch, right? That ease of use comes at a cost. The source material we're looking at analyzed a simple program written in both languages. And get this, the version written in C ended up creating a machine code file that was 40% larger than the handcrafted assembly version. It's that classic trade-off, convenience versus pure efficiency. So when you boil it all down, bringing a device to life is this incredible story of translation. It's about taking a human idea, structuring it logically, writing it down in a human-friendly language, and then using these amazing tools to convert it layer by layer into the basic ones and zeros that the hardware can finally understand. And that leaves us with a pretty interesting question. As our programming languages get more powerful and compilers get smarter, we move further and further away from the machine itself. So in this big rush for convenience and speed, do we risk losing the deep understanding that comes from speaking directly to the silicon? It's definitely something to think about.